touching the lip level of the siphon. So in that case, and this is going to occupy a mixture of air and water in the form of bubbles, and it is completely going to deflect, and this water from the outlet side also is going to move into the hood portion in this case. Still further, when you have an increase in the flow, for all these three cases which we have just looked upon, the water has not moved above the lip level of the siphon. It is still below the lip level of the siphon. So now when it's further increase in the flow, because the water is getting discharged onto the downstream side, so there is a space for the air and water to have an interaction in between. So this is something which we call in terms of simulation, or something in terms of multi-phase analysis or multi-phase flows. That means air and water is going to have a mixture of it. So in that case, when there is a still further increase in this sort of flow, you can see the complete hood portion is filled with water. But one point to note here is that the water is well in line with the lip level of the siphon. It is not above the lip level of the siphon. This is an important point to note down here. Here in this case, if you see the complete hood portion, the outer line of the hood portion is completely filled with air and water bubbles. This stage is called as air partialized flow. And this is where your air regulator siphon spillway is going to take an important role. So complete hood is filled with water, and the outer line or the inside of the outer line of the hood is filled with air and water bubbles. Let us say there is after this case, if you still further encounter the increase in the water level, now the level at the lip of the siphon starts increasing. That means there is an increase in the level of water here. And in the next stage, you will not be able to see any trace of air or any vacuum that could be present in the hood portion. And it is completely filled with water without any trace of air. That stage is called as black water. This is what is black water flow, where the level of the water has risen over the lip level and there is no traces of air which is seen in the hood portion, and at the same time the complete hood portion on the downstream side, the outlet on the downstream side and the inlet is completely sealed only and only with water. So these are the 5 different stages of the siphon spillway. Now, as the level of the water reduces, you can see the normal action of your weir or deflected flow or drowned flow or air partialized flow can still continue. That means there's nobody who is going to operate the gate over here in order to dispose of the water depending upon the, it's just doing by its own, and it is completely self-priming. So in that case, any small reduction will again encounter the previous cases. So based on this sort of functioning, siphon spillways have gained a lot of importance. In one is when you have a reduced width of the spillway, there you can use it, and especially when human interference is not possible at all. So these are the cases. So this is where the functioning of the siphon spillway takes place. And when you look at the discharges, at even the classification also can be taken with respect to the discharges, you can see that whenever you have less than 5 feet per second, this is the unit discharge I'm talking about here. It is something called as weir flow. If it is less than 9, we call it as deflected, drowned. We have air partialized flow. Air partialized is where air regulator siphon spillway is all about. Then you have black water flow when completely the hood portion is completely filled with water. No air traces. So in this context, some design aspects with respect to the height of this, that means the throat section, and the radius, at what radius do you have to go for your hood portion of the siphon, again plays a significant role over here. So then in that case, these are the some of the nomenclature which we adopt here. A is the throat height, and this is what is the inner radius and the outer radius. You can say this is what is the area of water to be entering, and also the air to enter. This is where the lip level of the bucket, lip level is taken. And this is the head over on the upstream side. So how do we calculate discharge? How do we estimate the maximum discharge? Because there is a classification of flow based on the discharge also. So when we take this, the discharge per unit with this taken based on the radius parameters which I have showed you just now, and the average velocity is estimated with this. This is what is the approach velocity we take, because normally when we go for analysis in any numerical or any software modeling, we have to take in open channel flows. We normally encounter the approach velocities. So that is another point. And whenever you have this average velocity falling less than your approach velocity, then you have to look into how you have to restrict your outlet section, and how to reduce the height on the upstream side, the elevation of the water on the upstream side. So these are the two constraints which you have to look over when your velocity is falling less than the approach velocity, which is a very, very, very important parameter in any open channel flows. Now, based on this, I just told you that I wanted to demonstrate this by means of an study which we have taken out. Here, the main objective of the study was to experimentally test the functioning of siphon spillway with various discharges using physical modeling. And then we have integrated that with numerical modeling, and we have tried to plot the flow that is taking place right from the upstream side onto the downstream side over the crust of the spillway. We wanted to test and compare the numerical modeling and results with the experimental results. So this was the basic objective of the study. And looking at, whenever we start some study, it is obvious that we need to look who has done it past. What were their limitations, or what were their study results? What was the conclusion which was given with them? When we started looking back to the literature regarding this air regulator siphon spillways, we have not found any exclusive literature that was targeting the comparison with the numerical modeling and the simulation experimental physical modeling analysis. So most of these two were the basic papers that we have studied in depth to extend our knowledge and see how best we can contribute to a different sort of analysis for using air regulated siphon spillway. So both of them were basically oriented towards physical modeling only. And nowadays, if you see the present scenario, like corona is prevailing, people are not able to move from their places. Now, in this sort of situation, we can't expect, because all Pune, CWPRS, and we have here Engineering Telangana Engineering Research Laboratories, all they do physical modeling analysis a lot for any basic hydraulic structures, huge hydraulic structures, because they first test it and then they start go for construction after all analysis has been done. Now, in this situation, the scenario is going to completely change, where most of the people cannot move at some coming to one place. They cannot have interaction, or they cannot move on the same place in crowds, and can't take up work from one to other. This is a different situation. In that situation, I thought that simulation analysis have to be given more importance in that case, rather than going only for physical modeling analysis. So probably they can look into the simulation analysis first, that is some sort of numerical modeling or mathematical modeling, and then they can go for this physical modeling wherever it is required or wherever it is important for them to understand in depth. So based on this critical reviews which we have seen through the papers that we have studied, so we have taken this task to study the more focus towards the simulation analysis, and try to tell them that even simulation analysis also will help you to provide the same sort of results as that of the experimental analysis. Let us move this is what is the setup where we have conducted the experimental studies. And I wanted to make a note over here that I wanted to thank Rajiv Gandhi University of Technologies uh, to have maybe enabling us to do the experiments over there. They have this facility of this apparatus, and they have allowed us to do the experimentation over there. Thank you so much for them on from this platform. Also, I would like to thank them. So this is where we have conducted. You can see this is what is the crust level of the spillway. This is the hood. This is the lip level where the water is trying to enter, and you can see here completely it is in the form of a round nappy. You can see this complete space, but picture is not clear, but there is still some space over here on the outlet side. It is not completely a deflected nappy case, nor it is completely a drowned case. So somewhere in between both, but the nappy of the structure is still drowned. So in that case, the water is been still moving on to the downstream side. It is not moving back. Whenever you encounter a flow back at this outlet section, probably we call it as the deflected nappy. So in that case, this is these are the measurements of the siphon, the experimental setup that we have made use for this analysis, physical modeling analysis. The instrument was made of acrylic material. The siphon model, which you can see here, was made of acrylic material, and the base and aluminium was, and this is a transparent glass through which you can visualize the flow. And here in this case, we have tested with many discharges, out of which these 4 discharges we have taken care for further analysis. And the discharge was measured using volumetric analysis. And very important point to note here is that you can see we try to plot the water surface profile from the upstream onto the spillway and then probably onto the downstream side. So here, in order to get this, the upstream and downstream, we can go for measurement using the point gauges. But the crust of the spillway, over the flow over the crust of the spillway, also have to be taken care in order to have the flow profile to be plotted. So for that, what we did was we have taken a flow visualization process in order to read and plot the depth over the crust of the spillway. So these are some of this is one of the experimental studies, and these were the discharges that we have carried out. So this is one part of the traditional way of doing some study. Now I just want to take you to a different platform where we have studied simulation. We know that simulation is nothing but artificially modeling the geometry or creating a model and applying all the conditions, including the equations, and then doing the test or trying to estimate various properties. Now, when I talk about the simulation, it is not a patent for any particular branch. It is being utilized or it has been adopted for various sort of engineering, even biomedical engineering, even it is used for aeronautical, mechanical. They have this simulation analysis most widely carried out. So in that case, this way of simulation, rather than going for your physical modeling, this also will try to create an experience as though you are doing a physical modeling analysis itself, because there's nothing which you are deviating from anything. We are trying to just model the physical model that is available in computer and just try to apply the same conditions. But whenever we say a simulation or whenever we talk about any flow, most of the flows that are encountered in any water resources applications is what is turbulence, which is very difficult to catch, which is very difficult to analyze. Turbulent flows are basically very irregular. They are more diffusive in nature. It leads to dissipation of the energy. They because they move it in. When we talk about in terms of equation, we have velocity and pressure mostly governing any type of turbulence flow. So when you have this turbulence created, so in this case, simulations can be used for a wide range, or wherever you have turbulence also. In such case also, you can use this by means of application of different models, by using different analysis methodologies. You can use different algo solver techniques and all these things. And one more important point is that, as I was talking, where siphon spillway is also adopted, where you can reduce the human interference. This sort of simulation analysis on a whole also will be able to reduce the effort of human. In a sense, one person or two persons sitting and completely understanding will be sufficient rather than completely going for a physical modeling analysis. Next is that, of course, the basic important requirements are a high-end computer, because when you wanted to run some large models, large size models or large project models, then probably you need to have a high-end computer. So that is one of the basic requirement. And second requirement is where you have to look for the software, and answers is mostly a commercial software that is available. And this software is only, these are the two basic requirements. If you have these two, probably you can understand and analyze. And just for the sake of uh, comparison purpose, whether, because any software can give you any result, whether that result is correct or not, probably you have to justify. So for justification process, we need either a very good analytical result of a particular case study, or, as of now, I have shown you one sort of experimental analysis which could justify that whatever simulation analysis results you have obtained are probably satisfying with the traditional traditional methods, that is your hand analytical methods or your experimental studies. Then in case, as I was talking, most of the flows are turbulent, and they are very much, turbulent flows are very irregular, diffusive. That means they try to deviate from the boundaries, and their energy is dissipated, in the sense that the smaller eddies try to gain the kinetic energy from the larger eddies, and in this form it gets dissipated. So as you see here, there are two terms basically which are going to govern. That is, one is your kinetic energy, the other one is your dissipation rate for turbulence models. So whenever you have high Reynolds numbers, we say it is turbulence models. So in order to solve this sort of turbulence, we have a very good governing equations, which are uh, the Navier-Stokes equations are adopted in order to solve this sort of turbulence criteria, where all your pressure and your velocity values are in terms of mean and fluctuating components. So when you have fluctuating components, then it is difficult to have analysis. So you have body forces, you have pressure forces, you have viscous forces, and you have the change with respect to time, the velocity component. So these two have to be properly analyzed. For that, by means of turbulence, we try to apply the averaging process for this Navier-Stokes non-linear differential equations. And this averaging process creates or gives us the other new equations, which is called as Reynolds average Navier-Stokes equation. Now, when we have this averaging process done, so all this is because we need to know only, we are interested in only the average components, but not the fluctuating components. So most of the turbulent flows, most of the engineers will orient towards understanding the averaging properties of the fluid. So in that case, when we apply averaging with respect to time, then we will encounter this Reynolds average Navier-Stokes equations, which will add additional terms into this. So when these additional terms are added to this uh, general traditional Navier-Stokes equations. So if you see, the diagonal parts are all normal stresses and other all shear stresses. Now here, there is a term which has come into picture is the shear stresses. This is called as turbulent shear stresses or Reynolds stresses. So in order to solve this Reynolds stresses, where there is an additional equations that have come into additional terms that have come into picture. So there are only three terms, basically three equations that are available, but there are additional terms that have to be solved. So in order to solve these Reynolds stresses, we try to apply some modeling to it. That means the models are adopted in order to have a solution for these Reynolds stresses. That means once you have number of equations equal to number of unknowns, probably it's very easy to solve the equations. So in order to solve these additional parameters, which are called as Reynolds stresses, we use models. Those are called as turbulent models. We have Prandtl and all other great people have given us so many models that can be adopted, because all nonlinear differential equations cannot be solved simply by using hand computations. Some mathematical modeling technique have to be adopted for it, so that probably we will be able to solve and get our own result. And now, in order to have these turbulence models, we have various types of turbulence models. That is one equation model, two equation model, zero equation model, one equation model, and two equation model, and so on. Zero equation model are simple algebraic equations. They can be easily solved for any sort of case. One equation model is applied where it gives you the rate of, just a second. One equation model helps you for this mixing length hypothesis, and it gives you a good relation, and it can be applied only for simple cases and not complex studies. So rate of transport of kinetic energy and dissipation. So when you have further wanted to know about the mean flows of in different directions, or when you wanted to apply this modeling analysis for complex cases, then probably two equation model is the best solution for it. Where among the two equation models, we have this K epsilon model and K omega model adopted very widely, because K epsilon model and K omega model are easy for the analysis, and it gives you the maximum information about the velocity and pressure parameters or any properties that you wanted to evaluate for a particular case study in a particular domain of the boundary condition or a control volume. So in this case, you can see these are the equations, partial differential equations for kinetic energy, and this is the partial equations for K epsilon and K omega. So the first term on the left hand side details you the rate of change of kinetic energy or dissipation rate. The second term gives you the transport of the kinetic energy or dissipation rate by means of convection. The first term on the right hand side gives you the details of the transport of the kinetic energy or the dissipation rate by means of diffusion, because diffusivity and convection are the basic properties of the turbulence. So then this is epsilon, that's going to give you the rate of change of destruction of the dissipation, and the last term is the production of K and epsilon, that is your kinetic energy and your dissipation rate. The first basic governing equations that any model uses is your continuity, momentum, and energy equations wherever it is applicable. And the second is, in order to know about the average properties of the flow, we have applied the Navier averaging for these Navier-Stokes equations, which has given us Reynolds average Navier-Stokes equations. That made us to encounter a new sort of parameters, which is called as Reynolds stresses, and those stresses are solved using these models in order to have a closure to the problem. This is normally whenever we apply model, it is called as closure to the problem in order to solve these additional parameters that have been encountered. So in this case, for applying all these, here in the present study, we have used ANSYS software that provides a wide range of formulations that can be possible. ANSYS gives you two different models. One is your computational fluid dynamics, the other one is your structural dynamics. So these two are the different modules that are available in ANSYS we have made adopted the computational fluid dynamic module, and this it is a science which gives you the numerical solutions for all the governing equations whichever we have seen: the turbulence models, the Navier-Stokes equations, the partial differential equations, the continuity and momentum equation. So in this case, the space is not is a constraint over here. The time is not a constraint over here, because when you start go for a physical modeling, it takes so many months to do it, because you need to have space for it, and also it takes so much time. But when you look for a simulation analysis, this with respect to the time and with respect to the space, both it is advantageous. And this computational fluid dynamics has various advantages, apart from, as I told you, if you have those two requirements, your computer and the person having knowledge regarding the uh, running of the software. So probably if that could be there, it will solve. The detailed understanding about the physics of the problem is also very, 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 very important. So in this case, it provides the ability to theoretical, that's what I just told you, that this computational or this mathematical modeling or numerical modeling analysis helps us to have a barrier between where we can't, when it is not possible to go for physical modeling, there this becomes a very good solution. And second point is that when you go for physical modeling analysis, it is not possible to visualize or estimate all the parameters. Or suddenly, if you wanted to have a change, let us say, as I told you, the design constraints, when your average velocity is not greater than your approach velocity, or if it is less than approach velocity, then probably I told that you need to constrict your outlet section, or you need to reduce the height of the upstream side. So when you wanted to do that, probably in physical modeling, again, there are some limitations over there when you go physical modeling analysis. But when it comes to this numerical modeling analysis, it is very much feasible for you to change. And also the flow process, how it takes place, the particle movement tracing, all these also can be visualized in a very better manner, uh, rather than the physical modeling analysis. I am not arguing that physical modeling is not required, but I'm telling you, wherever physical modeling has some sort of limitations to be carried out, in that case probably you can go for simulation analysis first, and then go for your physical modeling only and only if it is required. So now this CFD has a methodology to be followed, and this methodology goes with three different processes. One is the pre-processing stage, processing, and post-processing. Pre-processing is where you know on what geometry are you going to apply. Let us say, for example, I showed you one setup. You know what is the length of the channel, you know what is the width of the channel, you know what are the dimensions of this spillway, you know what is the height of the hood, and all these different measurements of the physical setup are known. So then in that case, you need to create a geometry. Then probably the geometry has to be refined in the sense you wanted to apply, because we have a control volume of applying or studying the required parameters. Those complete parameters have to be created with some sort of meshing. That means we discretize, which is called as control domain. We discretize the control volume into different cells. That means that each cell, we are going to apply all the equations, whichever are applicable, like your continuity, momentum, then your turbulence model equations, all are run at each cell, and subsequently it follows throughout the domain of the study area. In this case, in this sort of computational fluid dynamics, or when you look at finite element method or finite volume method or finite difference method, these are the three different ways in which the CFD analysis can be taken out. But when you wanted to have clear visualization of volume of the flow that is taking place, here probably we have made use of finite volume methodology that is suited for the study which we have taken, or the case study that is applicable. So next, that is where the geometry is created, a meshing is done. That means the complete section is discretized. The second section is, once your domain is ready, you need to apply some boundary conditions. That means you need to let the system know from where the flow is entering in and from where the flow is moving out. That is what is the minimum basic requirements that have to be given as a boundary conditions to the model. So once the boundary conditions are given, now you have to start applying your equations by means of the minimum value or only one value that is available with you, either pressure or velocity. So with this, we can begin you can start your solution. Then once your solution is done, then we will go for post-processing process, where you can visualize all the types of requirements. Like you can see how the flow is taking place. You can give animations as we do it in AutoCAD. We can give even animations to this. You can see the flow which is taking place in the form of vectors. You can see the flow which is taking place in the form of contours. It is not only the, let us say, if water here, as we are talking with water and air, the multi-phase analysis, two different flows. You can see the clear visualization of where is your water, where is your air, where is a mixture of both is going to take place. So all this, whatever results you want to evaluate from the analysis, you can do it in post-processing process. So now coming to the first, let me detail you in detail the one and all, in the sense that by each one. Pre-processing, as I told you, this is where you can create the geometries. You can see here, geometry can be created in three different ways. One is that you can use your normal AutoCAD drawing, convert it into JPG file. Your 3D modeling or 2D modeling, it is both are possible. 2D modeling is possible in ANSYS. 3D modeling is also possible in ANSYS. CFD is little comfortable with 2D, all sort of 2D analysis and small cases of 3D analysis. But when CFX is another module, other solver methodology that is available for us, which will be used for the 3D modeling cases. You can have stationary, you can have moving, or you can have any sort of analysis that can be done in CFD. So now coming to the geometry, one is that you can create your geometry either in 2D and 3D in AutoCAD, and then import that file into ANSYS, which is called as ANSYS Workbench, into a geometry file, and then probably you can apply your meshing and other processing. That's the first way. Second form of creating your geometry is Gambit. This is what is in Gambit. Okay, the second spillway figure is done in Gambit, which is not used right now. Earlier, before 2011 or 2012 rather, it was in use because it is a very comfortable tool where you can create the geometry. It is just like you give your points. If you know all the coordinate points either in 2D or 3D, you can give all the points. You can see this plus marks are the points first which are created. Then probably once all your points are created, then you will start joining all these points by means of line, by means of arc, the common draw commands that are there, SP line, polyline, all these are still available. As of you have it in AutoCAD, you still have them even in the Gambit also. So now you join them, all these points, once your outline is done with all the points, once your coordinates are given, the points are done, then you can probably join all the points with lines. Then the second stage of meshing is also possible in Gambit, which is not possible in AutoCAD. AutoCAD only you can create the geometry and you can import it into ANSYS file. Here you can even have the meshing also done. Then probably then you can go further for import that mesh file into your ANSYS, or you can even import the geometry also into ANSYS, and you can give and run your next stage of giving boundary conditions and then moving further for your analysis. These three figures which I'm showing on the top, like your square section, this is what is the flow that is taking place over a distribution chamber. in 2D. This is a pipe analysis which we have carried out for regular and for the round curved version. So these three are the geometries that are exclusively created in ANSYS workbench. ANSYS gives you a module which is called as design modular. Once you click on that geometry, it will open a window which is called as design modular. There's something which is called as ANSYS workbench. In that, you can create your geometry. So the first stage is creating the geometry. I'll just brief you the options that are there in the ANSYS, or once you start your CFD analysis. Then probably first is your geometry. Once after your geometry is done, that is automatically moved into meshing. That is another meshing module will be open where you can give all your meshing options over there. So these are the various forms where you can create your geometry and do your further process. This is what is meshing I was talking about. So you can see this is the complete structure on which you have to do your analysis. The whole domain is divided or discretized into different components. Cell size, you can have your own cell size. And one more point here is that when you wanted accurate results, probably it was observed from my experience that your mesh size should be as small as possible. That means in the complete domain, you can see here, this is more coarser mesh and this is more finer mesh. So wherever your interest area is there, there you can make it fine mesh so that your analysis will move. Because see, all those partial differential equations, non-linear partial differential equations and partial differential equations have to be solved by means of iterations. So the number of times you run on different number of cells, the more accurate will be your result. If you have a coarser mesh, I am not telling it is not correct or it is not possible, but the more approximate will be your result. When you wanted to compare, let us say I got X here, there also probably I wanted to have X. So in that case, the more accurate will be your mesh. We call it as something called as mesh refinement. There are many papers where which designs the skewness ratio, which gives you the statistics of number of nodes, number of elements, and all these things. So meshing is a very, very important criteria next to the geometry generation. And I just wanted to tell you one point in geometry that the even in AutoCAD also you will experience this, that the edges have to be properly coinciding. Even you have a small gap, the mesh, the geometry that you have created in ANSYS will not be properly getting imported into your meshing module. So it means that there is somewhere you have done, you have to make it a surface if it is a 2D, and if you have make a volume if it is a 3D. So all these things have to be done in the geometry process itself once you wanted to extend your domain or your study area or your case study to the meshing process. So once this meshing is there, as I told you earlier, all your continuity, momentum, equations, energy equation, and all your turbulence models equations will be solved. This is what is each cell. So in this cell, probably all the equations are run and then it is imported to the next. So likewise, this iteration process moves on till the end of the domain until your solution is obtained. So these two are your pre-processing stages. Now coming to the processing stage in the meshing itself, in pre-processing itself, boundary conditions. As I was telling you, you need to let the system know where is the inlet and where is the outlet. So this is a small channel where we have done our hydraulic jump analysis. So this is what is the complete, this is the same dimension as of we have it in the lab. Any of your labs have this open channels or tilting flumes on which you try to do all your wear notches and your estimation of coefficient, all these things, hydraulic jump. So this is where is the channel. This is what we have initialized is as inlet, where the flow starts moving, and this is the outlet, because as it is shown in the longitudinal direction, something we call it as front view. So in this direction, I have made this also as pressure outlet because I feel it is the surface is open to the atmosphere. So pressure outlet, we have different boundary conditions here. Velocity inlet, velocity outlet, combination of inlets and outlets, the boundary conditions that can be applied. You have pressure inlet, pressure outlet. Velocity inlet can also be what you can say combined with this pressure outlet. So your velocity inlet and pressure outlet are most widely adopted boundary conditions for any simulation analysis using your CFD. Then after this, once your geometry is done, as I told you, we have Fluent, and other one is your CFX. Fluent is a solver, okay, from where your mesh is imported into this Fluent launcher. So this is how the first slide looks like when you have 2D. If your geometry is 2D, probably the 2D gets highlighted. If your geometry is 3D, because once when you're doing it in ANSYS itself, in ANSYS workbench as for geometry and for meshing, probably once the third stage is your setup. Fourth is solution. Fifth is your results. These are the 5 basic parameters that you can see when once you open your ANSYS CFD. In that, you will have all these 5 options: geometry, meshing, setup, solution, and results. So we have seen geometry and meshing. Now this is where your setup is going to start, and you will run all the equations by using some solver methodology. So this is under the processing. The solution and your results come under your post-processing stage of your CFD methodology. So you can have here your double precision, meshing mode, or all these options you can have. These will be by default will be checked in. And this probably you can use it as serial or parallel. Normally we go for parallel, and here we go for double precision. Once after this you click OK over here, your mesh is completely imported into the Fluent along with all the boundary conditions. Now here what you have to do is, in this stage of setup, once your model have completely imported into this, you need to give your materials, like means whether you are working with water, whether you are working with air, whether you are working with oil, fire, what it is. So you need to initialize your materials. After that, even you can initialize the material through which these flow. That means there are solid and fluid. These are 2 constraints over there. Solid, you can give, as I told you, that you need to initialize the material properties also through which the flow is taking place. There you can probably give your aluminium, wood, or there are by default certain amount of parameters are already available. You can check, or you can select from them, or even you can initialize your own material by means of user defined function. You can give your own material. Probably you have all the properties like your temperature, density, and thermal coefficient, all this. There are some parameters, there are some properties that are required in order to initialize your own user defined function. Once after your materials are done, now the system have to run all the equations using a particular solver methodology. Why solver methodology is required here? Normally, when you have all the flows are, we say, incompressible flows, until unless it is a different case, when we, other than water or any other thing, we call them as incompressible flows. The common problem that is encountered with incompressible flows is that it is very difficult to solve or satisfy the continuity equation in that. So in order to, because when we start applying the continuity equation also have to be satisfied, because it's the basic constraint and the momentum equation. So here in this, what we try to do is, in order to satisfy the continuity equation for incompressible flows, we have a particular method called as pressure correction method. And we have different solver techniques that are available, like we have simple, simplex, Pisco, and all these are. What is simple in the sense? Semi-implicit method for pressure linked equations. This is simple solver methodology. Normally everybody adopts this because it requires less space, it is faster, and all these things. So we also have applied the simple methodology. What is that solver algorithm that is run behind the simple and the solver methodology is what is pressure correction method. Now what is this pressure correction method? Pressure correction method is where, as I told you, the continuity equation cannot be satisfied. It is difficult to satisfy the continuity equation. What we try is, we try with an initial assumption of a pressure value. We try to put that pressure value into the momentum equation, solve the momentum equation, and get the velocity values like u, v, and w. Substitute these velocities values back into the continuity equation and see that whether it is satisfying. If it is not satisfying, the change in that pressure is again taken into consideration. Again, the momentum equation is run. Take the velocity values that are obtained from the momentum equation, then put it back into the continuation. This repetition of iterations will be taken place unless the continuity equation is satisfied. Once after that continuity equation is satisfied, that value is taken at one cell. That value is probably taken into the next cell. So this continuity, momentum, and your energy equation, if it is used, so these three, and along with, once your continuity equation is satisfied, it will run your model equation which you have selected, whether it is k epsilon, k omega, or in k epsilon also, that is 2 equation model, 1 equation model. You have 0 equation model, simple algebraic equations, and also can be possibly solved using this sort of software. All these, once your solution is converged, that means once it is satisfied with all the cells, you will get a statement that solution is converged. It means that all the equations are satisfied at that particular cell. Then this process repeats and continues until it completes all the cells in the given control volume. So this is the solver methodology, and which is called as pressure correction method. And here the solver using this pressure correction method is what is your simple semi-implicit method for pressure linked equations. So once this is done, and as I told you, this is the process that takes place. Now, as I was briefing you, we have three methods that can be adopted. That is your finite difference, finite volume, and finite element method. Here we have used finite method. It is a common approach when we have multi-phase analysis. It is very easy to visualize. Then it has an advantage of the memory, and you can run for high Reynolds numbers. Okay, or partial differential equations. There is one. They are iteratively solved simultaneously, or one after the other. You have pressure-based solver algorithm, then you have density-based solver algorithm. You have to decide which one could be appropriate for your case, so that the equations will be run one after the other, or all the equations will be run simultaneously. So in this case, it also helps us to have, it gives us some macros. Now, when I say finite volume method, that means that we can clearly visualize the volume of flow. Now, for example, in my case, it is water and air. I am more concentrated, or my interest is to see that how water is moving from the inlet point to the outlet point, what is its height, and all these things. So, as I told you earlier, every software gives you the visualization, some result, but whether that result is correct for you, or whether that result is matching with your own traditional methods result or not, is not possible just by visualization. So then probably these macros, not only for volume fraction, you have it for velocity, you have it for pressure. That means macros, in the sense you need to write a program which is assigned to the domain of the area or the case study which you are working out. It will give you the numerical values of that. So you should write a code in C language. So that code you have to run using these macros. There are so many macros available, all different types of pressure, for dynamic pressure, for you can have x velocity, you can have y velocity, for each and every parameter that you will be able to visualize by means of your contours and vectors. For each one, you have a macro which is run to know the numerical values of that particular flow that is going to take place in the control volume. So here in my study, we have made use of this volume fraction because I am interested to plot the water surface profile. So for plotting the water surface profile, as you have seen for the experimental analysis, I will be able to easily measure my upstream side and measure the downstream side flows. But when it comes to the simulation analysis, only visualization will be possible. So for that case, macros will be helpful for you to know the numerical values by means of a code written, and it is to be executed into the solution process. So then you will get your numerical values so that you can plot the required parameters of turbulence. So now this is where which we have the same domain that is seen in the experimental setup. The same thing we have modeled. This is where I have shown you the gambit one, and even workbench also we can do. And this is where I have shown you only a reduced figure, not a reduced one, a cut figure probably. Here you have your upstream side, that is inlet, and here probably in this corner you have your downstream side, because I am more interested to know how is the flow which is taking place over the crust of the spillway, because the dimension of the channel is large. So in that case I have uh, zoomed my location to this. So you can see the mesh over here is more finer when compared to the mesh on the upstream and downs, because my area of interest is only the head over the crust. So in this case, as I told you, this is what once you have initialized for, as I told you, we have either you need to give your velocity values or you need to give your pressure values. So these two values, depending upon if you have your pressure values to be initialized, you need to give it as pressure inlet and pressure outlet. If you're going to give your velocity value, the boundary condition at the inlet should be your velocity inlet. So in this case, here we have taken velocity inlet and pressure outlet as my boundary conditions, and the rest of all are taken as walls. Whichever I am not going to initialize with inlet and outlet, all rest of the things by default will be taken as walls by the ANSYS. You need not separately initialize until unless you have a specific constraint over there at that particular edge or that particular face. If it is 3D, the complete face of the inlet will be initialized as the inlet, the complete face of the outlet. So according to your requirement, you can have the change of, but initialization of boundary condition have to be done well before in the meshing case itself, after meshing itself. So now when you start doing this, what you will try to, this is what is iteration graph that is given once you run your equations on the complete mesh, which you can see here. So the solution gets converged. The statement which I told you that the solution is converged will be given right from the beginning. But you cannot stop at that point. You need to run your model or continue the calculation process until unless you will be requiring you will encounter your required flow that is possibly shown by means of in this geometry. So in that case, this is the iteration graph, and these are the number of iterations that were carried out in order to see the flow visualization and in order to evaluate the numerical values. So we have stopped at 15,000 iterations because whatever flow we were requiring was arrived or achieved. So then probably we have stopped at that stage. So after this, this is what is one setup process. Now we will move to solution. That's the fourth stage of your ANSYS. Now in the solution, as I told you, you can see all these contours like your volume fraction contours, you have your velocity magnitude, you have your pressure, you have static pressure, dynamic pressure, total pressure. There are so many, you have turbulent viscosity, you have turbulent kinetic energy values. So once you have your result, or once you have some analytical estimations carried out, you can probably compare them. Here I have just measured the upstream side and measured the downstream side using the experimental setup, and have a visualized flow over the uh, crust of the spillway. So probably I am interested to see how the flow is taking place. Now here, this is what is a legend which you can see for volume fraction. Now volume fraction is 1, because we are using here finite volume method. Volume fraction, water is taken as 1. That means there are two cases now: primary fluid, secondary fluid. Primary fluid, if you're interested in air as a primary fluid, normally for aerofoils. So for that we use both air. So how is your air going to move around the aerofoil? So in that case, one type of air is the primary liquid that, or fluid, or primary material. Second is also an air. But in this case, in most of the open channel flows and pipe flows, we have water or oil or any liquid that is moving, that becomes the primary. So in my case, water is primary, air is secondary. So when I say primary as water, the primary liquid is initialized with 1 and the secondary liquid is initialized with 0. And anything in between 0 and 1 is the mixture of these two phases, that is multi-phase, air and water. If you see the legend over here, the complete blue color is 0. That means it is air in my analysis. And the complete red color is given as 1, which is water. So anything which you can see here about this sort of line is what is the mixture of both air and water. We are not interested in the mixture, but we can visualize that. Now, okay, I have seen this. I know that there is a depth over here, some sort of depth of water on the upstream side, some sort of depth in the over the crust of the spillway, and some depth on the downstream side. Fine, but how to take out that result? I say, okay, flow is taking place. But when I wanted to have some numerical values for this in order to compare exactly my understanding of simulation analysis with experimental results, something else have to be done there, as I told you, in the form of macros. So these are the contours. Now, all your solution is done. Now I'm moving to the results part, that is your post-processing part. All this is done in the third stage, which is called as post-processing. And these are all the contours. You can also have vectors to be given, and this is most important for any of the finite volume analysis. So from this, you can see a graph is plotted. We have adopted both the models, the K epsilon model and K omega model. And for all, we have calculated the approach velocity. And for this approach velocity, we have estimated what is the upstream depth here using the macro. As I've shown you, C underscore VOF is the macro, which is adopted to write a code and probably run it by executing it inside the model, and we will be able to get these values, and we will be able to plot the complete. That means you can see here, there is a complete flow here. So as we are running in between 0 and 1, so whatever your interest area is, suppose let us say I wanted to know the volume fractions in between 65 to 70%. That means 0.6 to 0.75. If you initialize this percentage of your volume fraction values, you will get all the values which are there right in the complete domain in between those 0.65. Because you can also see there is a legend over here which starts with 0 and 1. And there are values which will fall between 0.6 and 0.7 or 0.65 or 0.7. But here in this case, when you exactly want to know the flow of water, you should take the value very near to the 1. That means that it should be something like 0.95 to 1, or still more precision, it can be 0.98 to 1. So very, very near to 1. So using those volume fractions of your own interest, probably you can get this type of graph that is possible, and also you will be able to estimate the height on the upstream the flow that is taking place over the spillway, over the crust of the spillway, and also on the downstream side of the spillway. So these are the results which we have obtained by using the macro run and by two different models, and these are the upstream and downstream values. Now that was one stage. Second stage was we wanted to test it. By default it will be smooth metal surface. We wanted to test it by taking the properties of acrylic also. So using this acrylic properties also and using the smooth metal properties, we have done the analysis three times. That is one with normal, second with smooth metal surface, third with acrylic surface, acrylic properties. Because the acrylic properties are with the complete setup of your siphon spillway. And the base of your channel is aluminium, that is smooth metal surface. So we wanted to test it whether the model is giving correct results or not. So in that case, we have initialized, because acrylic material properties are not available in the answers. So we have initialized our own properties, and we have looked upon the variation of the flow that takes place with these two different materials, and the graph that was obtained probably was matching with the our own result that we got it with the normal k epsilon and k omega model using these two metals also. So now coming to, so we have seen that probably when we use simulation analysis also, the results that could be probably obtained can be made use when you have proper justification or when you have proper comparison done with the traditional methods. So looking at this, coming to the result part of the case study, we have taken the discharge from 4.3 to 7.4 different discharges. The types of flows that were possible with the experimental setup was weir flow initially, and then as the flow got increased, it went to deflected nappy condition. So types of flows, among the 5 different types of flows, these were the types of flows that were possible for the siphon spillway that we have taken into. So when we have compared the results were far less than 5% when compared with, not that less than 5%, they were less than even 1% with the experimental results and the simulation analysis, both for upstream and downstream. That is what where we were able to exactly measure with the experimental setup by using the point gauges attached to it. So in that case, with that only we have compared the results of the simulation analysis also, so that we will have some idea whether how best the software is giving us the results. Both the models I have shown you, the K epsilon model and the K omega model, were giving the similar results when taken with the analysis. So now this graph shows you the different forms of the comparative results of the experiment and even the K epsilon and K omega values for all the 4 discharges. So I just wanted to conclude here by saying that the technology improvement or the available softwares can be made best utilization in order to solve any sort of problem by means of simulation, and it will also provide you a best result depending upon, one is that you have complete understanding of your domain, you have complete understanding about the physics of the problem, you have a complete analysis from where your flow is exactly moving in and out, or at what is your interest of the parameters that you're going to try to evaluate. Now here I have just used the macro only to look into the depth parameter. Other parameters, as I told you, when you have velocity, which I have applied for the other case studies, I have used the macro of velocity. I have used the macro of dynamic pressure, where you can have a beautiful graph obtained with different values throughout the profile of the first spillway. We have adopted this velocity magnitude macro and dynamic pressure macro. In this case, I would like to share with you that we have solved uh, almost all these applications, like your search tanks, where we have taken this Kalvakurti lift irrigation scheme as one of the case study, and we have studied the search height that is going to be possible in the search tanks. So that we have studied using the simulation analysis, and it gave us very good result when we started comparing it with the analytical result. And one more I wanted to share here is that the search tank analysis analytical uh, analytical process or methodology also was not available anywhere. Experimental studies were done by IIT Bombay and others. And so with that, we try to give an analytical methodology, and then we have compared that analytical methodology with simulation analysis using the same computational fluid software and same using the finite volume method. We have done it for spillways. We have given a new equation. I try to give a new equation for estimating the uh, projected length, that is a jet projected length after when the jet is ejecting out of the spillway, what distance the jet is going to strike on the downstream side. The length and the height of the jet we try to give a new equation for it from our study. And sluice gate, as I told you, we have tried to estimate the hydraulic jump, length and height of the hydraulic jump using the macro. We have carried out a rectangular notch analysis, that means the water surface profile for rectangular notches. And then pipes also we have studied sudden closure, what will be the how the pressure, how the velocity is going to move, what are the velocity vectors to it, where it is converging, what is vena contracta place, where the uh, flow is getting converged. So all these things we have done the estimation of cover also for circular and double D bridge using some physical. All these depending upon the availability of the equipment. As I told you, this ARS's experimental analysis we have done in IIIT Bassett, RGKUT Bassett, and where for spillways we have done the comparison with analytical analysis, whatever is available with us. Hydraulic jump we have done in our own lab, rectangular notch we have done in our own lab, sudden expansion and contraction. Bridge POs also we have a basic hydrology model in which we have the setup for cover, estimation of cover for different types of weirs, like your rectangular weir, your circular weirs, piers, and all these things. So there we have done airfoil. We have done it using wind tunnel. We have a very big wind tunnel which was kept into use for estimation of the simulation of flow profile over the airfoils, pipe bend. Then we have done it for canal head regulators and for distribution channels. In some are in still pipeline. We are still working out with different open channel and pipe cases using the same methodology, try to test it and get the results. So this in this present scenario where we can't avoid the movement of we can't allow the movement of people, so there probably this will not hinder your work. This will provide you, this sort of analysis will provide you a better results. You can still even we heard that CWPRS is also carrying out simulation analysis and giving the results, taking out the results for different cases of hydraulic structures which they are going to test it. So in that case, this could be a very good tool, and it will be a good contribution towards the society in order to maximally eliminate the utilization of your physical modeling analysis. So in this case, I would like to thank each and everyone for patiently listening to my presentation. And probably I hope I have given you a little bit of information regarding the simulation analysis. Now it is open to the forum for any questions. I'll be happy to answer, and also I'll be very happy to learn from you all if I have to add something to my study, which I'll be able to carry out for my future applications. Thank you, sir. Sudesh sir, now you can take the forum, please.
Thank you very much, madam, for your nice presentation. It shows your dedication towards the subject and as well as your presentation
Yeah,
also.
sorry, I
Very
just
much.
wanted to add one more point. This much I was able to tell, which I'm very, very sorry that I didn't mention it in between. I got it, but I forgot. I should thank from this forum, I would like to thank my supervisor, Professor Suresh Kumar sir, who made me to solve all these applications and who made me to understand in depth of this software and made me to do so many applications in it and try to give me so much of knowledge in form of my PhD. So I would like to thank him wholeheartedly that he is the one person who is behind all these things by making me to learn all these. And thank you so much, sir. I thank you from bottom of my heart for making me to be capable to stand in this form and try to solve all these applications. Thank you so much, sir. Yeah, Sudhir sir. Thank you.
Thank you once again, madam. Thank you once again. Yeah. And by this presentation, I think we had learned how the ANSYS is important in solving the open channel flows or as well as various types of components. It's really a very good presentation, and the participants also feel very happy after listening your presentation, madam. Just
Thank you,
a
sir.
small question has been raised from one of the participant, Arvind.
Yeah, yeah.
How would you find the siphon spillway radius? Is there any range for the velocity design?
We have given you, I just move back. Here, velocity over the put portion should be 12 meters per second. Because see, here in this case, yeah, maximum velocity on the crust is assumed as 12 meters per second over here. Okay. And as I told you, based on this design part, okay, and the height of the throat, probably you can look into this constraint and you can design it. There is a ratio here which R2 by R1 depending upon the maximum discharge. Let us say either discharge will be there for you or the crust of the spillway will be there for you. Depending upon that, you can have the analysis of the other one. No, not all the parameters will be unknown in these equations. So either one is known, the other can be estimated. If you want, I can now I don't exactly have the information with me. I just let you know if somebody is having any queries. I gave my mail ID at the last also. Probably I can answer them. So any one parameter is possible, the other can be known.
There is another question, ma'am.
Yeah.
Out of the two models, that is omega model and epsilon model, which one
Yeah.
is suitable?
Sir, very good question. Even I had this question when I was starting my work. Actually, K omega and K epsilon both are two equation models. And both have the same constraint in the sense that dissipation rate there is epsilon, here it is omega. But it is going to solve the kinetic energy first. So whenever we do analysis, we start normally with K epsilon. K epsilon is the most widely adopted model. That is the first model which you have to use it for your analysis. Now, K coming to K omega, it is a little bit a different form of dissipation value that is going to be given. So in that case, as I've shown you the equations, both the equations have the transport, destruction, dissipation, and convection properties. These are the normal turbulence properties which both the equations can solve it. So normally everybody, so because I have done so many applications, so I have seen the papers also, and the literature also says that K epsilon is the best model. You use it, then probably you can compare those results using K omega also. Because same model you apply, you just change the model type there. That's all. It's nothing. So you can use both. Nothing is inferior or nothing is superior than the other. Common, that is what I told, commonly widely adopted is K omega, K epsilon model.
I hope, Mr. Arvind sir, your questions has been answered.
If somebody can add something to me also, it is most welcome. so
Yeah,
that I
if
can.
you raise your hands, just we will unmute you. Then you can ask the questions directly to the madam.
Sir, you have a very huge crowd of participants. Very happy to see them. Almost
Yes.
180.
Yes, madam.
Ramanjaneyu sir has a doubt.
Yes, yes. Sir. Just I am going to unmute you, sir. You can ask the question.
Hello, good afternoon, madam.
Yeah, good afternoon, sir.
Madam, thank you for nice presentation, madam.
Thank you
Madam,
so much, sir.
I have one doubt, madam.
Yeah,
This
sir.
ANSYS software can we use in concrete, madam?
Sir,
Concrete, nothing
answers
but
you have structural dynamics.
structural dynamics.
There's another compound, other module. And in the beginning only I told you have structural dynamics module and computational fluid dynamics module. Once you buy answers, you will be given these two modules. If you're
Okay.
interested only in CFD, what we did was 4 years back, we took a licensed software which has 5 licenses of structural dynamics and 5 licenses of computational fluid dynamics.
Okay.
Both structures
Dynamic.
and water resources can work.
Okay, okay. Madam. By using this
Answers you can use, sir. You have, what I heard from my colleagues is that answers is going to give you a nice break structure, it seems. So they were also more interested in answers.
Okay.
But
Madam,
one thing, sir, I want to add, there we use finite element method most widely adopted.
Okay, okay. In structural analysis, finite element method can be used.
Yes, sir. Finite element is most widely adopted.
Yes, yes, madam.
Here we most widely use finite volume for our own water resources problems. We use finite volume more.
Okay, okay, madam. Thank you, madam.
Madam, another question from the Arvind sir.
Yes, sir.
For these types of design, should we use only ANSYS or any other software can be used?
Can I ask what types of designs he wanted, or the question is not very clear.
Okay.
I'm sorry.
Sir, Arvind sir, just I request you to unmute yourself and you can ask
designs for answers. Can little bit elaborate on the question, please?
Okay, madam. Just I am going to.
You just repeat the question, Sudhir sir, so that if I can get something, I can answer.
For this design, we should use ANSYS or any other software.
No, this design is what is the big question mark which I have.
Yeah, that's right.
That is giving a contradictory statement. This design in the sense what? Like just now, Ramanjaneyu sir was asking that can we use answers for structures? So there is a clear, this design in the sense I'll have little doubt. I am not able to get the point which sir wanted to ask.
Sir, Arvind sir, just unmute yourself and you can ask the question directly to the madam. Madam, sir is not responding.
Okay, I just answer in my way. What actually maybe it is, whether it is going to correctly give his give the answer to his question or not, I don't understand. I don't know, but still I wanted to answer. See, answers, as I told you, it can be adopted for structures and it can be adopted for water resources. Mostly, if I say CAD/CAM is a software which is adopted for mechanical. Now, as I told you, we have taken up so many applications and we have done it in computational fluid dynamics. In structures, you can use abacus, or for some analysis, you can use abacus. See, what design, it is not with the design, it is with the requirement of the properties that you're going to look for. Now, when I am interested to see how a flow is taking place over the profile of the spillway, I wanted to see how the flow is taking place over the profile. So in that case, if I use finite element or abacus or any other software, Pro-E, all these are different types of softwares that are available. So if I use that, probably my interest of knowing the depth of flow or the profile flow, I will not be able to encounter. So probably you need to select according to the properties you are going to target. or what is your objective all about? As I told you in the beginning only, that CFD uses finite difference, finite element, and finite volume. But I'm not interested in finite element and finite difference. I was interested in finite volume because I want to see the volume of the flow in multi-phase analysis. So in that case, my requirement of this will maybe not be satisfied, because I can't say, because I have not used it, may not be satisfied by using finite element and finite difference. Maybe I may get it in a different form. I'm not telling we don't get it, but we may get it in a different form. So in that case, my interest here is volume, so I have dedicated it to finite volume. So any design or any analysis targets with the objective you're looking for. So accordingly, you can go for the usage of the software. So this is which I understood that sir wants to ask. So probably there was some other hand which was raised for a doubt.
Sir, I am going to unmute you. You can ask your question, sir. Hello.
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 Madam,
Yeah,
you can ask the question.
Good evening, ma'am.
Yeah, good evening, ma'am.
And this session is more interesting. And I just want to know that is there any possibility of sharing the PPTs or recordings?
That you should ask the coordinator of the FDP.
Okay, ma'am. And this is very informative session.
Okay, thank you so much, madam.
Okay, thank you, ma'am.
I'm very happy to hear such nice words. Thank you so much.
Thank you, ma'am.
Madam, just on behalf of many of the participants, they are requesting to share the PPT. If you are willing, you can share it, ma'am. As you wish. There is no compulsion.
Yeah. See, there is nothing to hide or nothing to give off like that. So with minor changes, probably I have oriented in the way I wanted to tell you all. Probably with minor changes, I will share it to Sudhir sir. Probably he will be able to share it to others also.
And
minor changes.
Madam, one question from my side, madam.
Yeah, sir. Yes, sir.
Actually, we have so many mathematical modelings. First of all, we have a MATLAB. Which also we can build so many number of mathematical models by assumptions or whatever so case it is. So in what way ANSYS is different from the MATLAB, especially for these types of the designs?
Sir, according to my understanding, because I should say very frankly that MATLAB I have not used.
Okay.
Last day I was speaking to one of my colleague that I wanted to learn MATLAB also. What I heard is MATLAB is purely a program-oriented software. Okay, here we are not writing any program. All the equations are inbuilt. Okay, like whatever model you use, accordingly it is going to give you the result based on whatever your requirement and whatever your initial input is all about to the model. So there I am not sure, I can't answer you incomplete, but what my understanding is that I am not sure that you will be able to visualize the process of flow that is taking place exactly by means of one or two parameters. It is completely, and geometry, here we are, see, one point which I wanted to tell here is that, sir, we are creating a geometry over here. That means it is exactly replicating the prototype. It's a model. Now, on the model, we are applying the same conditions. And as far as MATLAB is concerned, if I am wrong, please correct me. I think we need to write the program over there and give the conditions like discharge, L is equal to so and so, width is equal to so and so. But I have very limited answer for this particular question. MATLAB will not going to survive the complete 100% result for when compared with ANSYS. it gives you a different form of result. This will give you a different form of result. That much I
Okay.
can tell.
Okay, okay, madam. I understood. Sir, are
If
there...
I am, because I didn't work with MATLAB, sir.
Okay, sir. Okay, madam. No problem, madam. Sir or madam, are there any questions from your side still? Yeah, one question like dynamic pressure in open channels using ANSYS.
Dynamic pressure. You wanted to know dynamic pressure. Is that the target, the objective is to know the dynamic pressure?
I hope it is like that, madam.
Ah.
Actually, the question is the dynamic pressure in open channel using ANSYS.
Yes, you can evaluate any parameter, sir, for any domain. I have showed you out almost 10 applications, almost less than or equal to 10 applications. For all those applications, I am not targeting at only one point. Now, I'll tell you one simple example, like spillways we have taken. We have taken the Nagarjuna Sagar Dam. For that spillway, we have evaluated the dynamic pressure, velocity, magnitude, the depth of flow that is taking place in the bucket of the, what you can say, I just forgot. The trajectory jet that is going downstream side of the spillway. What is the crust level on the top? How is the dynamic pressure going to vary over the throughout the profile of the spillway? Each application gives you a different parameter. And even as I told you, when you have your results open or when you have your contours domain open, there probably you can see very clearly what are all the parameters you can get it. You can get dynamic pressure also. Absolutely. There is no doubt in that. You can get dynamic pressure. But one important point is that dynamic pressure only in the form of contours you will be able to visualize. As I have shown you the contour of volume fraction, you can see the velocity, magnitude I have shown. Even dynamic pressure also can be seen. Here in this particular application, dynamic pressure is not at all a constraint for us. Where we have done spillways, there our target was dynamic pressure. Because when we look into cavitations and all these things, dynamic pressure have to be evaluated for spillways. So that is where even dynamic pressure also can be evaluated. Ramya madam has some doubts.
Just I will unmute her, madam.
Yeah.
You can ask the question.
Madam,
Ramya madam, tell me.
I'm having one doubt, madam.
Yeah,
Just now you said dynamic pressure, no, madam.
yeah.
So, అక్కడ మనకి నెగిటివ్ ప్రెషర్ కూడా క్రియేట్ అవుతుంది కదా మేడం?
అది negative pressure create అయినప్పుడు wherever you are encountering negative pressures, then probably you will get negative values. You will see the legend as I was showing you. The legend for, yeah, just a second. This, as I was showing you for this case, and for velocity magnitude, you can see the red color is what is the more maximum velocity which is encountered here. So in the same form, you can see your dynamic pressure values also ranging from the least to the maximum throughout the domain of any application. So somewhere you are encountering negative pressure, it will also show the negative pressure, provided you should have encountered that negative pressure over there. Practically also it is possible. Here also, if it is a case of encountering negative pressure, you will be seen very clearly the values in the legend. You can see that also.
Okay, thank you, madam. I thought negative pressure, if it is creating negative pressure, I think it is wrong.
There are some cases, see, spillways, especially Ramya, why I'm calling Ramya is because she is my own student. So that is what I'm calling her Ramya. Don't mistake the other participants. So Ramya, the case is that here, when you have cavitation encountered, that is because of the negative pressure. So whenever, let us say in the case of spillways, it becomes a very, very, very important parameter over there, the negative pressure. So there probably when your cavitation is possible for that particular problem, obviously the same thing you're going to model here, right? So then
Yes, yes,
if
madam.
analytically you get negative pressure, this also should give negative pressure. If it is not giving, then it becomes a big question mark. Then probably you have to think what might be the reasons. How you have to change your model. How
Okay.
best you can match. Change is not manipulating. How best you can match to the existing conditions of the prevailing situation of that particular spillway, and you can give the values, and you can see how whether the values of the legend are moving right from at the bottom. If it is negative value, right from the bottom negative, you will be given the values, and it will move to the maximum. So bottom is the least, top is the highest. So that means
Okay.
red color is the highest one, blue color is the least one in anything. But see, here I'm looking at velocity magnitude, so my values are in meters per second. Here I'm looking at volume fraction, where it is dimensionless, so it is giving me in the form of decimals. That's the difference.
Okay.
You can get it.
Yeah. Yeah. Thank you, madam.
Yeah.
M- Madam, one more thing. How can we calculate this volume fraction? How can we get this volume fraction?
As I told you, there is a code written in C language. You have to
Okay.
use the macros which are given by ANSYS. We are not creating any macro. There are so many macros. All the macros are given for each and every component which the ANSYS gives you in the form of result. Using that macro, you need to write a code. That is what which is my own this thing. Until unless you write the code for
Hmm.
it, you will not be able to get the numerical values of any parameter which you are being targeting. You have to write the
Okay.
code in the form of macro in C language.
Okay, madam.
It's like a C
Thank you,
program.
madam.
Sir,
Thank
still
you very much, ma'am.
questions?
Yeah. Thank you so much, Ramya.
Madam, I hope all the questions has been answered from your
Yes,
side.
sir. Yes. I just stopped share my screen right now. Yeah.
Sure, sure. And once again, we thank you very much on behalf of our whole FDP GICT team. So
Thank you.
again, we are very thankful to you for your for sparing your valuable time in spite of your busy schedule. We accepted readily our invitation, and we are very thankful to you for that. And also, all the participants are feeling very much happy after listening to your presentation. And I think this also brings the importance of the simulation tool, especially in the case of various hydraulic structures.
Yes.
Yeah. Thank you, madam. Thank you once again.
Thank you so much, sir. Thank you so much
Valuable
for the
time.
opportunity given.
Okay.
Probably I was busy with my own webinar, which I conducted for last 3 days, Thursday, Friday, Saturday, so that I was little bit doubt whether I'll be able to satisfy the constraint of what your topic is all about, because your topic is so wide and so current situation apt topic. So
Yes,
I wanted to correlate with the topic. So that is what which I had a little doubt in my mind. So that is what which made me to take so much of time and give you the title only yesterday
Yes.
night.
Yes,
So
yes,
probably
madam.
I thank even Ramya also for
Yeah.
this opportunity, and Sudhi sir and head of the department also for giving me such a beautiful opportunity to expose myself, whatever knowledge, minimum knowledge I have in front of so large gathering. Thank
Yes,
you so much, sir. Thank you very so much. I can't express my happiness which I have because I am targeting over a larger, wide strength here. And I wish you all the best for the next 4 days, which you have been scheduled. And I hope all the sessions are very interactive. Thank you so much, sir. Thank you
Thank you
all the
very much, madam.
participants for having the patient listening, and hope I have answered to you all. And you can also even mail me. So this sir has my mail ID. If you have any doubts, I am free to connect to you all, and I can clarify whatever doubts you have. Thank you so much, sir.
Thank you very much, ma'am. Thank you very much, ma'am.
Right.
And the participants, just a small announcement that actually the feedback form will be kept in your WhatsApp group, and based on the session 1, session 2, and session 3 of this today's event, just we are asking your the feedback. After the session has been completed, the link will be shared through the WhatsApp, and you can fill in the feedback form. And with this session, just we are going the today's session. This is the end of this today's session, and tomorrow at morning 9:45 a.m. we are going to meet for the day 2 session. Thank you, sir. Thank you, madam. One and all.
Thank you, sir. Thank you so much. And bye, all of you. Thank you.